Hey guys, back for day 3 on limits and differential calculus topics. We're going to cover, you can see below, identifying horizontal asymptotes using limits, definition of this thing called differentiability. We're going to do some derivatives from first principles and then look at some of the rules of differentiation. So now we don't have to use limits, we can just use shortcuts. Awesome, let's do it. Okay, so if you're to think about a function and where a horizontal asymptote takes place, let's say a function has a, vertical asymptote here at -1 and a horizontal asymptote at y equals +1. Well, what we would see the function's behavior doing, right, is as the function approaches over here, the limit as x approaches positive infinity of f of x would equal 1, right? So we would see that there'd be a limit at infinity, right? So as x approaches infinity, or this other way, as x approaches negative infinity, we would notice a trend, right? So here, by definition, right, the limit as x approaches positive or negative infinity of f of x equals c indicates that f of x has a horizontal asymptote at y equals c. All right, so let's look at this first example. You'll see that I'm going to need to do some work here in order to determine what the horizontal asymptote might be, if there's one that exists. So I'm going to take the limit as x approaches infinity of the numerator. I'm going to expand that. If I FOIL that, I get 10x minus 15 minus 2x squared plus 3x. In the denominator, I just have 8x squared. Now I'm going to divide everything by the highest power, x squared, and see what happens. So I'm going to rewrite the limit, simplifying, and I'll see that I get 10 over x minus 15 over x squared minus 2 plus 3 over x over 8. Now what will happen as x goes to infinity is that each of these terms will go to 0. So this will evaluate to -2/8. Okay, so we would know that f of x has a horizontal asymptote at, not x, y equals -1/4. Now with a polynomial over a polynomial in rational form like we have here, you won't have to check both sides. Okay, you wouldn't have to also take the limit as x approaches negative infinity. But if you have an exponential, yeah, you're going to want to pay attention to that. Okay, so let's do two limits. Let's do the limit as x approaches infinity of e to the x minus 3 over 2e to the x plus 15. Now I don't have a special method for you in this limit, but what I can tell you is that as x increases without bound, these values of -3 and 15 become irrelevant. Okay, so in essence, this is not equivalent, but in essence, this is approximately the same as the limit as x approaches infinity of e to the x over 2e to the x, which, of course, you can see that the numerator would grow half as fast as the denominator. So I'd see that g of x has a horizontal asymptote at y equals 1/2. Now we got to be careful with exponential functions. We also got to test the other side. So as the function heads to the left forever, e to the x minus 3 over 2e to the x plus 15 what happens there is as x decreases, right? If I take e to the negative infinity, that's equivalent to 1 over e to the infinity. So that's approaching 0. So this term will approach 0, and this term will approach 0, twice as fast, to be exact. Okay? So I will be left with negative 3/15. So g of x has a horizontal asymptote in the other direction at y equals negative 1/5. Goofy function. Maybe take your calculator, graph it, see what it looks like. All right, let's move on to some more good stuff. All right, let's talk about the definition of differentiability. The definition of differentiability, f of x is differentiable at x equals a if f of x is continuous at x equals a. So in order to be differentiable at any point, the function has to be continuous. Now a function can be continuous but not be differentiable, but it can't be differentiable and not be continuous. Okay, this notation here in part 2 is funky, but all that this notation right here means is the derivative as we approach a from the left. So the slope of the function as we approach a from the left. Here's the limit version of that, right? So this is the limit definition of the derivative evaluated at a, coming from the left. Same thing from the right. So the slope coming from the right of a and the slope coming from the left of a both have to exist and have to be equal. My interpretation is that f of x is differentiable at x equals a if f prime is continuous at x equals a. Okay, so let's examine this graphically and then we'll talk about it algebraically. So show that y is continuous but not differentiable at x equals 0. Well, clearly here I'm looking at the absolute value. The function is continuous here at x equals 0. However, the slope over here is negative 1 and the slope over here is positive 1. So the slope approaching from the left of 0 and the slope approaching from the right of 0 do not match. Okay, so what I would do here is I would say, well, f of x as a piecewise function is equal to negative x, right? The line negative 1x if x is less than 0, and it's equal to positive x if x is greater than or equal to 0. Therefore, its derivative function would be equal to negative 1 when x is less than 0 and positive 1 when x is greater than or equal to 0. So can I show that f prime of x is not continuous, right? I know that f of x is continuous, but what about f prime of x? So continuity of f prime of x. Let's talk about that. Well, does f prime at 0 exist, right? That's the first thing I need to know. And the problem there is that it doesn't. It doesn't exist there, right? There's an abrupt change. Now, if we looked at this, though, we could also show that this fails as we approach 0 from the left of f prime of x. That equals negative 1, and the limit as x approaches 0 from the right of f prime of x equals positive 1. So it fails in really two ways. One, because, well, the derivative doesn't exist at the point. And two, because the limit as x approaches 0 of f prime of x does not exist, right? Proven here, because the left and the right-handed limit don't agree. So f of x is continuous. We don't have to really dispute that. I think that's pretty clear graphically. I could do this, right? I could do continuity for f of x and show using the steps of continuity, but graphically it's pretty clear. So let's move on and look at another example. All right, determine if f of x is differentiable at x equals 1. So a common mistake, you guys, is that someone will just jump directly to f prime of x, which is okay, right? I want to get there, but the first thing I got to do is prove continuity. All right, so f prime of x will be equal to negative 2x plus 5. Now, how did I get that? I took the derivative of this, and I've kind of stepped over, maybe over the topic. You'll see in just a minute shortcut rules for differentiation, okay? But I'm using a little bit of knowledge that maybe you don't remember from last semester quite yet, okay? So the derivative of 3x plus 10 is just a line, so its slope is 3. So here's f prime of x, and here's f. So some will jump to, well, is the limit as x approaches 1 from the left of f prime of x equal to the limit as x approaches 1 from the right of f of x, f prime of x, excuse me. And the answer to that actually is yes, right? I want to know if that's true. Well, it actually is. So negative 2 times 1 plus 5, is that equal to 3? And the answer is yes. So I can say that the slopes coming from both sides are the same. So is it differentiable? Well, I don't know. But the first thing you should always do is you should check to see if the function is continuous, because it might have the same slopes approaching at the same x value, but if those aren't meeting up at the same y value, we got problems. Okay, so let's check continuity of f of x. So first thing, does f at 1 exist? Well, f at 1, seeing that this would include x equals 1, would be negative 1 squared plus 5 times 1 plus 6. So f at 1 is equal to, oh boy, let's see, what would that be? 11, that'd be 10. Okay. Now we have to do the limit as x approaches 1 from the left of f of x, and we actually just did that by evaluating. Oh no, we didn't, excuse me. That would be 3 times 1 plus 10. So that limit is 13. And we actually just did the limit coming from the right by finding f of 1. Ends up being 10. Okay, so here we can see that the limit as x approaches 1 of f of x does not exist. And the reason for that is because these two values right here and right here do not agree. So what would this look like graphically? What the heck would this look like? Well, what it looks like is, here's a line, right? That's 3x plus 10. Here's the point x equals 1. We said that we got an output or a limit as we approach 1 from the left of 13. And then we have a quadratic that looks like this. So yes, their slopes here and here are both 3, right? They both have a slope of 3. However, the function's not continuous there. It's quite a crazy problem. So please check continuity of the original function first. Don't make the mistake of jumping straight to f prime. Okay, let's look at an example now. Example 3, g of x is continuous and differentiable. We're told that, so we can assume that that's truth. Okay, determine the values for a and b. All right, so if g of x is continuous, then I know, first of all, that g of 5 exists, but I know that the limit as x approaches 5 from the left of f of x, which in this case would equal, well, we'll do that in a second, and the limit as x approaches 5 from the right are going to be equal. So this would be the limit as x approaches 5 from the left of, well, from the left would be this function, ax squared plus bx plus 39. So I know the limit of that as that approaches 5 should be equal to the limit as x approaches 5 of 4x minus 11. So I'm going to plug 5 in for x and see what I get for an expression. So I plug 5 in for x, I get 25a plus 5b plus 39 is equal to, that would be 20 minus 11, which would be 9. All right, so I'm going to do a little simplifying. That would be 25a plus 5b is equal to negative 30. Okay, so using continuity, I know that this is true. So since the function was continuous, I know that is satisfied. Okay, let's look at differentiability. So with differentiability, I know that the limit as x approaches 5 from the left of f prime of x should equal the limit as x approaches 5 from the right of f of x, f prime of x. That means I've got the limit as x approaches 5 from the left of the derivative of this thing. Okay, and again, I'm skipping ahead, but the derivative of ax squared plus bx plus 39 will be 2ax plus b. Plus b. So that's 2ax plus b. The derivative of the other portion of the function will just be 4. So the limit as x approaches 5 from the right of 4. Okay, now what I'm going to do is input for x a 5, which would give me 10a plus b, and the limit as x approaches 5 from the right of 4 is still just going to be 4. And so I'm going to solve for b, although this is useful. Okay, I'm going to solve for b here. Let's put it in a different color. How about red? Yeah, let's do that. So b equals 4 minus 10a. I'm going to plug that in over here for b. So over here, now I'm going to solve. So 25a plus 5 times b equals negative 30. All right, so I'm going to plug in 4 minus 10a. All right, let's continue. So this would be 25a plus 20 minus 50a is equal to negative 30. We're going to solve for a here. So I'm going to subtract 20 over here and then combine these two like terms here. So it'd be negative 25a equals negative 50. It tells me a equals 2. Okay, so if a equals 2, star that, hang on to that. I'm going to plug 2 back in here and find b. b equals 4 minus 10 times 2. So that would be 4 minus 20. So then it looks like b must equal negative 16. Now, in some cases, you might get a quadratic where you'll get 2 possible values for either a or b, but in this case, looks like we get just 1 for each. Okay, let's keep it moving. All right, so let's talk about first principles. Right, first principle is also known as the difference quotient. Right, so the derivative of any function can be written as the limit as h approaches 0 of f of x plus h minus f of x. So let's do this. I'll rewrite it up here. Limit as h goes to 0 of f of x plus h minus f of x all over h. That is f prime at x. Okay, so let's look at the function that we're given. We're given 3x squared. Now, some of you might already know your power rule, and you probably figured it out from the previous page, but this should come out to be 6x. So let's use first principles in order to show that that's true. Okay, so here we have f of x plus h, so into 3x squared, I've plugged x plus h. Here's f of x over h. We're going to do this, work this limit through, and show that f prime equals 6x. Okay, so in order to do so, I'm going to have to expand this first term, so that'd be 3x squared plus 2xh plus h squared minus 3x squared all over h. Okay, so you're going to notice if I distribute this 3 to each of these terms, this first term, which will be 3x squared, will cancel with this term 3x squared. They'll reduce out. So I'll have the limit as h approaches 0 of 6xh, ooh, that looks good, plus 3h squared all over h. Now let me work my magic here. F prime going to factor out an h after I write down some limit notation. Don't forget limit notation, that's just poor form. 6x plus 3h all over h, and look at that. What reduces? Boom. So f prime of x will equal the limit as h goes to 0 of 6x plus 3h. Now if h goes to 0, then 3h goes to 0. Therefore, f prime of x, all that's left is 6x. Boom, shakalaka. That felt good. Okay, let's do this for a trig function now. Here's sine of x. Hey now, do you know the derivative of sine x? I do. It's cosine x. We're going to use a couple of special limits here in order to do this. The first of which we did in our last lesson. So sine of h over h, as h goes to 0, that's 1. The other limit that we're going to see here in a minute is cosine of h minus 1 over h, and that goes to 0. You should have done that in your homework. If you didn't, shame on you. Okay, let's expand this limit using, hey now, look at that, sine of x plus h. So compound identity with sine, so that'll be sine of x cosine of h plus sine of h cosine of x. So that right there is sine of x plus h expanded minus sine of x all over h. Ooh, bad person, bad teacher. Forgot my, oh goodness, can't erase that, I don't know why. Forgot my limit notation. Limit as h goes to 0. Okay, don't be a bad teacher. You're not a teacher, but don't be a bad one. All right, so I'm going to group some items here. I'm going to group sine x cosine h and sine x. I'm going to write this factoring out a sine x. I'm going to be left with cosine of h, ooh, hey now, minus 1. Okay, plus, I'm leaving sine h cosine of x alone. And what I'm going to do is I'm going to split this h between the two terms. So I'm going to put an h there, and I'm going to put an h there. Now using limit laws, I'm allowed, if I have a sum, to split this into two separate limits. Okay, just like this, plus the limit as h goes to 0 of sine of h over h times cosine of x. Perfect. Okay, so now check it out. The limit as h approaches 0 of cosine of h minus 1, this right here, is going to go to 0. Therefore, this first term will go to sine of x times 0 plus this limit right here goes to 1. So that will be plus 1 times cosine of x. And look at what we just did. We just showed that the derivative of sine equals cosine. Awesome. You may be required to potentially show that the derivative of cosine is negative sine using the same process, so I'd practice that. Okay, let's keep moving. All right, often seen shortcuts. Okay, memorize these. So the derivative of ax to the n, where a is a real number and so is n, right? That'll be an x to the n minus 1, just like this. The derivative, this is the notation for taking the derivative with respect to x, of 2x to the 5th would equal 5 times 2x to the 5 minus 1, which will be 10x to the 4th. Okay, so notation, right? This, if y equaled 2x to the 5th, then you could say y prime equals 10x to the 4th. You could also say dy dx is equal to 10x to the fourth. Or if it were f of x, then that would be f prime of x. Okay, lots of notation, all meaning the exact same thing. Okay, a few others. Derivative of the e to the x is itself. That one's great. Derivative of a to the x is ln of a to the x. Why wasn't this ln of e to the x? Well, it was because ln of e equals 1. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. That one I would memorize. I'll show you how to do it using the quotient rule. And derivative of ln of x is 1 over x. So let's get into, I don't know. Let's just see what's on the next slide. Yes, the rules. So we got product rule, quotient rule, chain rule. Product rule, here it is. I'm not going to read it all. Quotient rule, same thing with division instead of multiplication like product rule. Chain rule is nested or composed functions, right? Compositions of functions. So let's do one of each on the last slide for this lesson. All right, tan x. I'm going to show you how to differentiate, even though we already know that dy dx, all right? Dy dx equals secant squared x. Let's show it. All right, let's rewrite y as sine x over cosine x. All right, this is a quotient, right? It's division. So dy dx will equal the low function times the derivative of the high function. Derivative of the high function would be d dx sine x. Well, that's going to equal cosine x. Therefore, low times d high minus high times d low. Well, what is the derivative of the denominator? It's negative sine x. Okay, so I'm going to bring the negative out here, make that positive. Multiply by sine x. And divide it all by the low function, which is cosine x squared. Okay, so dy dx. Check out how awesome this is. This will be cosine squared x plus sine squared x. Does that ring a bell at all? This will be cosine squared x. Well, cosine squared x plus sine squared x, that's an identity we know. Cosine squared x plus sine squared x is 1, right? Using our trig identities. So dy dx is equal to 1 over cosine squared x. Well, what's 1 over cosine squared x? That's secant squared x. Hey now. Hey now. Cool. Using the quotient rule we just showed, that's good. All right, let's use a little chain rule here for number 2, p of x. All right, so how do I know I'm using chain rule? Well, I've got one function nested inside another function. So let's look at the chain rule itself. Okay, what is the derivative of f of g of x? Well, it's the derivative of the outer function while leaving the inner function alone times the derivative of the inner function. So in our case, what is f of x? Well, f of x is ln of x. What is g of x? G of x is sine x. So what I want to do is find f prime of g of x. All right, so the derivative of ln of sine of x. I'm going to take the derivative of the outer function, leave the inner one alone. So the derivative of ln is 1 over something. We leave that something, which is the inner function, alone, times the derivative of the inner function. Okay, so I did f prime of x and showed it was 1 over x. What about g prime of x? Well, g prime of x is cosine x. So I'm going to take 1 over sine x and multiply it by cosine x. What that's going to equal is cosine x over sine x, which then in this case, p prime of x will equal cotangent of x. Look at that. That's cool. Natural log of sine of x derivative is cotangent of x. Just awesome. Okay, product rule. M of x. All right, here's my first function. Here's my second function. So f times g, if I take the derivative with respect to x, is derivative of the first times the second left alone plus the first times the derivative of the second. So the first function is 2e to the 3x. Now this is going to require chain rule for its derivative. So the derivative of 2e to the 3x is itself. The derivative of the inner function, 3x, is 3. So the derivative of f of x is 6e to the 3x. That's kind of cool. So that's 6e to the 3x. We leave g of x alone. Square root of x. Now g of x is the square root of x, but I'm going to write it as x to the 1/2. So g prime of x is just going to use that power rule. I'm going to bring the 1/2 down in front and reduce the power by 1. So g prime of x would equal 1 over 2x to the 1/2 power, which if I put it back in radical notation would be 1 over 2 root x. Okay, so I would write f of x untouched times the derivative of g. And I get that. Let's clean it up just a tad. Let's call this m prime of x. This would be 6e to the 3x times square root of x plus 2's reduce. That'll be e to the 3x over square root of x. And there you have it, guys. We're going to get into some deeper differentiation in day number 4 and actually use derivatives to evaluate limits. Oh boy, get excited. We'll see you in the next video.